In this video, we're going to start to look at titrations and pH curves, and we're going to start to do it with a strong acid and strong base first. First, just a little bit of review. Remember, neutralization reactions are reactions between an acid and a base, and typically you're producing water and a salt in the molecular equation. And generally, they're actually going to have a really, really large K, a K much, much bigger than 1. So we're going to assume that if it were in equilibrium, it would lie so much to the right that we essentially are going to say that these are considered to go to completion. So if we were writing a strong acid and strong base, remember my net ionic equation would be H plus, would react with all the OH minus that's present and produce H2O. And I'm assuming this would go to completion. Notice that there is just an arrow pointed to the right. Okay, if I was to react a weak acid and a strong base, my net ionic equation would end up looking something like this, where the weak acid would react with all of the OH minus from the strong base, which would have completely ionized. However, the weak acid would not completely ionize, and I would get H2O in the conjugate base. And for a strong acid and a weak base, okay, the strong acid would completely ionize, the 100% ionize, the weak base would not, okay, and I would get the weak base reacting with all the H plus from the strong acid to give me the conjugate acid of this weak base. And we had done this back in chapter 4. If you wanted to go back and look at one of those videos, I do have a net ionic video if you want to go back and look at that. How do you know that neutralization goes to completion? Here's a strong acid and strong base. Let's just kind of look at the opposite reaction, which we kind of looked at more in this chapter. H2O breaking up into H plus and OH minus, or hey, wait, this is the auto-ionization of water. The K for this reaction would be Kw, which is 1 times 10 to the negative 14. So the K for this, which is the reverse, what do we do with K's if we flip the reaction? We take the reciprocal, so 1 over Kw, this would have a K equal to 1 times 10 to the 14, so a really, really large number. So we could say equilibrium would lie so much to the right. We're going to just assume that this goes to completion. Okay, much, much bigger than 1. Take a moment, as I said, we had done writing net ionic equations, but take a moment and do this for practice. Pause the video and then check your work. You can either write the net ionic right away, fitting into that template I just wrote before, or you can complete the molecular equation and then do the net ionic based off of your molecular equation. So this first one, strong acid, strong base, I know right away I'm going to get water. If we're looking at a molecular equation, I get water, H2O, and the salt, CaCl2, which happens to be soluble. But I can know for a strong acid, strong base, as long as my salt is soluble, I will always get this as my net ionic equation. Okay, for this is a weak base and a strong acid. This one's going to fully 100% ionize. This one will not. So this is going to react with the H plus, and that H plus is going to get accepted to turn this into its conjugate base, and really the NO3 is just going to be a spectator ion. So this is going to be my net ionic here. And again, feel free to actually write the molecular equation if you want, but I think it's easier to kind of fit it into that template that I showed before, or just to kind of think about it logically. This is a weak acid and a strong base, so this one would not 100% ionize. This one would into Li plus and OH minus, and it's the OH minus that would react with this weak acid to produce water, and then the conjugate acid after the H donates its, or the acid donates its H plus to OH minus. Okay, so a titration is typically you're going to have an acid of known concentration being added to a base of unknown concentration, or vice versa. It's a way of figuring out the molarity of one of your missing pieces, whether the molarity of the acid or the molarity of the base. And in this situation, you're typically going to use either an indicator or a pH meter to figure out when you've reached what's called the equivalence point. The equivalence point is the point at which all of your H plus from your acid has reacted with all of your OH minus with your base, and it's been neutralized completely. Okay, remember at the equivalence point you can use this equation where you can get the moles of H plus by taking the molarity of the acid times the volume of the acid times how many H pluses are in that acid or being donated by that acid. And you can get the moles of OH minus by doing the molarity of the base times the volume of the base times how many OH minuses are being accepted by, or OH minuses are in that base. So if it was like calcium hydroxide, which has 2 OHs in there, you would be timesing it by 2. The end point in a titration is the point where the indicator changes color. Notice that these have 2 different definitions. So typically you want the end point to be around the same as the equivalence point, but these actually have 2 different definitions. So when your indicator changes color is your end point. When all of your H plus is neutralized by your OH minus or vice versa, that's the equivalence point. The plot of pH versus volume during a titration is called a titration curve, and we're going to see this a lot in AP problems. Okay, so we're going to take a moment and look at a titration curve for a strong acid, strong base reaction, something like HCl with NaOH, strong acid, strong base. Okay, so if I look at this, here I have pH on my y-axis, I have volume of base on my x-axis. And if I notice, I start with 0 milliliters of NaOH. So right away I can see that NaOH is the thing that's being added into my beaker drop by drop by drop, little by little. In my beaker to start with, I have all acid. Notice that the pH is 1. So the initial pH for this strong acid, strong base titration is just going to be based on the initial concentration of HCl that I have at the start. Okay, and then little by little I'm adding NaOH, and what I notice is that it doesn't change that much at first, because really I have excess acid in my container. I'm adding some base. Whatever base I add immediately gets neutralized or reacts with the H+, and that's why this pH is not changing. However, as I get to the equivalence point, it rises slowly. Then once I get toward the equivalence point, it jumps dramatically at the equivalence point. A drop of acid or a drop of base could change it either way and really alter that pH substantially at that point. Okay, the pH at the equivalence point is 7. Does that make sense for a strong acid, strong base? Let's think about the salt. Okay, the salt would be conjugates of a strong acid and strong base would have negligible ability to act as an acid or base, so that's why the pH would be 7, because you have a neutral salt when you have a strong acid, strong base. Okay, then the final pH, okay, at the end, now I'm adding more base, and all of the acids already been reacted, so here I have excess base, and the final pH here would be based upon how much sodium hydroxide you have in excess in your container. So notice if I have excess acid in my container, I'm going to have a low pH. If I have excess base in my container, I'm going to have a higher pH. And here you show indicators. Phenolphthalein would be a nice indicator to use. Methyl orange could be a nice indicator to use. We want to choose an indicator that changes color in the portion of the graph where the pH is changing rapidly, somewhere around the equivalence point. We want the end point of the indicator when the indicator changes color to match around the equivalence point. Okay, you can always answer you can always figure out from one of these titration curves the volume of base in this situation, because this is milliliters of NaOH, that was needed to completely neutralize the acid. I go to my equivalence point, I drop down, and I see that 50 milliliters is the volume of base that would have been needed to completely neutralize the acid. So if I were doing that equation, that MAVA number A equals MBVB number B, 50 milliliters would be my V base. So you might have to get that off of a titration curve. If I were doing the opposite, where I started with a base in my container and added an acid, you would just have a flipped titration curve, except that, so you'd start with a high pH, you'd end with a low pH, but your salt at your equivalence point would still have a pH of 7. So for strong acid, strong base titrations, there's no equilibrium to consider because both your acid and base completely dissociate. The only reaction that's going on is your neutralization, your H plus reacting with your OH minus to give water, or your acid plus base giving water plus salt if you want to look at the molecular equation. However, you do need to always figure out what moles remain in your container after the acid-base reaction, and then use that information to determine the pH. So you always have to think about what remains. Hint, hint, meaning a lot of the times it might be a limiting reactant problem. Okay, so again, just going through this titration curve, your initial pH, if you have to find your initial pH, that's completely controlled by your initial acid. You're just looking at your initial acid concentration. You can use that to figure out your H plus concentration, and then use that to figure out your pH. Along here, your pH is going to be controlled by how much excess acid you have. So it's not going to be the same concentration as your initial concentration. Some of it is going to get used up by the base that you're adding. So you've got to figure out, well, how much acid is left in your container, and use that to figure out the pH. Okay, here is your equivalence point for a strong acid, strong base. It's always going to be 7 because of your salt. Your salt is a neutral salt if it's a strong acid, strong base. And above here, your pH is going to be controlled by excess base. So in this situation, you have to figure out, okay, how much base do you have remaining in your container after it's reacted with the acid, how much base is left, and then do your pOH and then pH based on that. Okay, so let's look at an example. I'm telling you to start with, there's 50 milliliters of 0.2 molar nitric acid, which is a strong acid, and it's titrated with 0.1 molar NaOH. And I want you to determine the pH at these exact points. So if you have a problem on like an AP or a test, you're probably not going to be asked for the pH at every one of these points, but you might be asked for one of these points, so you've got to know how to do it in each of these different scenarios. And you might say, hey, can I just go over and use this graph? Yeah, but I want to show you, based on calculations, how you can also get an exact answer. So initially, what's in your container? Okay, it's the volume of base that you're adding. So initially, it's just your acid in your container. Okay, remember it's a strong acid, so it's going to completely 100% ionize into H plus and NO3 minus. That's the only thing present in your container to start with before any base is added. So the initial pH is just going to be based on the concentration of H plus. So take a moment and solve for it. Okay, so if I have a 0.2 molar solution of nitric acid, that's also 0.2 molar of H plus. So if I just do the negative log of 0.2, I get 0.699. So that's my pH. Okay, let's look at the next situation. pH after 10 milliliters of the base is added. So now it's actually a reaction that's happening. I have this acid, and it's reacting with 10 milliliters of 0.1 molar NaOH. But hey, what kind of problem is this? Neutralizations occurred, but it's not a complete they're not completely using each other up. One of those reactants is going to be in excess. It's the acid that's going to be in excess, and that's why if you look at the titration curve, it has a lower pH still at that point. We've got to figure out what remains in the container. It's a limiting reactant problem. The pH is going to be based upon the excess H plus that remains. Not that gets used up, but that remains. Okay, based off of your neutralization. And if you're more comfortable writing a molecular equation, HCl plus NaOH goes to H2O plus NaCl, that's fine, but I'm going to look at it as a net ionic. So I'm just going to figure out the stoichiometry. I'm going to use essentially an icebox just so you can see my work organized, and you can feel free to use an icebox for this. I changed it to write ICR instead of equilibrium, the R for being what remains in my container, and I'm going to make sure I work in moles for this, because if I'm doing stoichiometry for this reaction, I want to be in moles since these are in different containers to start with different volumes. So I'm going to be in moles for this. So the H plus is coming from the HNO3. Sorry, I said HCl before, but it's HNO3. So there's 0.2 molar of it, and there's 50 milliliters, so that's 0.01 moles of H plus I have to start with. And the OH minus, it's only 10 milliliters added so much so far. There's 0.1 molar of it, so that's 0.001 moles. Okay, what's limiting? Hey, obviously the OH minus is limiting. I have less of it. Okay, if I wanted to just fill in my change, this would be minus X, this would be minus X. I don't care about the water. And what would remain is 0 moles of OH minus, because that's what's limiting. That's what's going to get used up completely. So what's my X? My X is 0.001, because 0.001 minus X equals 0, so X equals 0.001. So I would take off 0.001 from this, do 0.01 minus 0.001, and I would get 0.009 is what remains of my H+. And again, you don't have to organize this in terms of an ice box, in this case ICR box, but do make sure that you change your molarities into moles, and do make sure you figure out how many moles of H+ are left in your container. That's what you're going to base your pH upon, because you don't have your starting H+ anymore. You now have less of it because some of it reacted with your base. Now I can find the pH. Just remember, hey, I'm in moles of H+. Let's turn this into molarity. Okay, if I have 0.009 moles, I've added the 50 milliliters. I had 50 milliliters of the acid to start with. I've added 10 more milliliters of solution, so I'm over 0.06 liters, and I get 0.15 molar, and if I do the negative log of that, I get 0.824 as my pH. So again, the lesson is you are doing a limiting reactant problem. You are figuring out how much H+ you have at the end remaining, and that is what you're using to get pH. Just make sure you do change into molarity before doing the negative log. Okay, at the equivalence point, hey, if it's a strong acid, strong base, automatically 7 because I have a neutral salt. The only species left are the salt and the water, and your salt in this case is neutral. pH after 150 milliliters of base is added. So again, I have some acid to start with. I have base being added. This is a limiting reactant problem. At this point, you're going to be governed, your pH is going to be governed by how much excess base is in your solution. So you always got to find out what moles remain in your container after the reaction first, and then you can figure out your pH from that. Okay, so again, this is a limiting reactant problem. I'm just going to organize this in terms of an ice box. I changed E into remains, and I'm going to be working in moles because I have two different containers with different volumes and different molarities. It's going to get messy if I'm not in moles. So again, my H+ to start with is the same as before. My OH- that has been added now is 150 milliliters of 0.1 molar, so 0.015 moles of OH- from my base is being added. So it's now my H+ that is my limiting reactant and getting completely used up. So I know this is 0 at the end, so I can see, hey, X must equal 0.01. I could take 0.015 and subtract the 0.01, and I have 0.005 moles of OH- left. So I'm figuring out what remains. This is not the only way you can figure out what remains. You can do it in terms of dimensional analysis and stoichiometry, but I'm organizing it this way for you. Feel free to do the same or not, but you must be figuring out how much remains. Okay, so this is in moles. To do pH, I need molarity. So the molarity of OH would be this 0.005 moles over the combined volume of what's in my container now, the 50 milliliters to start with plus 150 milliliters. And I get 0.025 molarity. If I do the negative log of this number, it gives me POH, so don't forget to subtract that from 14 to get my pH. pH is 12.4. That makes sense. If I have excess base, it should be basic. So do make sure that your pH logically makes sense. Okay, so important note, notice you must always figure out what remains, which is based on the stoichiometry of the neutralization. To do this, you must always convert to moles first. The acid and base have different volumes and are coming from different containers, so moles and molarities are not interchangeable. You can figure out what remains with an ICR box or stoichiometry, but you must be in moles. And that's why I specifically changed it to ICR, just to remind you, hey, it's a different box, be in moles instead of molarity. And then after, you may have to convert to molarity for pH calculation. Okay, let's also get another practice in aside from doing just calculations. Let's get in some conceptual practice, looking at a titration curve, being able to figure out what kind of ions are present at different points along the curve. So take a moment on the next curve. I want you to do a couple things. The following diagram, label what ions are present at the 4 different points along the graph. And then determine which ions or species would have the greatest concentration at these 4 points. At the initial, between initial and equivalence, at the equivalence, and after the equivalence. So take a moment to do that, pause the video, and then check your work. Okay, This is, so again I said it's a nitric acid and it's being titrated with NaOH. NaOH is being added dropwise into the system. So to start with, in my container I only have the initial acid, which is a strong acid, and it completely 100% ionizes. So my species that are present are actually H plus and NO3 minus. I actually don't have HNO3 altogether as a molecule. I will not find that at all in my solution. I will find the H plus and NO3 minus separated 100% completely ionized. Okay, between my initial and my equivalence point, I have excess acid, okay, and I am dropwise here, slowly but surely adding NaOH. What is out of the NaOH, which is a strong electrolyte, would 100% ionize into Na plus and OH minus. Would both of those things remain in solution? Well, the OH minus is going to get immediately used up and react with that H plus. So really what I have in my container along this point is my initial acid still in excess, and that's completely 100% ionized, H plus and NO3 minus. And I'll have Na plus, which is being added solely from the base. The OH minus from the base is getting used up completely, neutralized and turned into water, so I won't find that in solution. And I didn't put H2O, but these are all aqueous, so you could assume that there's H2O present. Okay, so those are the main species that are in my solution. Okay, the OH minus would be negligible in compared to the amount of H plus. So as I go along here, okay, my amount of H plus would slowly be decreasing because it's getting used up and reacting with that OH minus. The NO3 minus would be staying, the Na plus would be slowly going up because I am adding NaOH, so I'm slowly adding more of it as I go along. And the NO3 minus would be staying the same because it's not reacting at all. It's just a spectator ion. It's hanging out and watching the show. Whatever I had to start with is still there. At the equivalence point, that's the point at which the moles of H plus and the moles of OH minus have completely canceled each other out. So I won't find either of them as a main species present, but I will have my salt, my neutral salt, my Na plus and NO3 minus. The NO3 minus is there from the initial acid. The Na plus is there from what I've added to the base. Those are not reacting. They're just sitting there watching the show. Okay, and then beyond here, I'm adding more and more base. So beyond here, not only do I have my salt, but now I also have excess OH minus, which is being added from the base, and even more Na. Notice I don't have H plus as a measurable ion here, really, because that has been completely used up and neutralized, and no more has been added after. Okay. As I go along here, my amount of Na plus would be slowly increasing as I add more and more of the base. Okay, the OH minus would be increasing. Na plus would be greater than OH minus because none of that reacted, and some of the OH had already reacted, but it would slowly be getting higher, and the NO3 would be staying the same. So just to kind of give you a clue of what's going on in terms of ions in your solution. To answer the question here, determine which ions would have the greatest concentration at A, the initial point. Well, that's your strong acid would be there and fully ionized, so it would be H plus and NO3 minus. Between the initial and the equivalence point, okay, the NO3 minus would be the one that has the greatest concentration, because though I had H plus and NO3 minus to start with, as I add base, the base is going to react with the H plus and use some of it up. The NO3 minus won't react at all, so the NO3 minus will always have a greater concentration than H plus between the initial and the equivalence point. And I'm be adding Na plus, but it wouldn't be as much as the initial NO3 minus yet either. Okay, so the excess acid, but H plus is getting used up, NO3 minus is a spectator. At the equivalence point, it would be your salt. Your salt is in a 1-to-1 ratio, NaNO3, because they each have a +1 -1 charge. So it would be Na and NO3 the same. And after the equivalence point, it would be Na plus. I've added excess base, but some of the OH minus had reacted with the H plus, so I'll have less OH minus than I would Na plus at that point, because Na plus is just a spectator ion and it hasn't reacted at all. Just as a reminder, you can have the opposite kind of titration curve where you start with a strong base and it's being titrated with an acid, you'll start with a higher pH. The pH would be controlled by the initial base. Just rather than an acid problem, you have a base problem. Okay, your pH between the initial and the equivalence point would be controlled by the excess base you have. It's a limiting reactant problem. Figure out how much base remains, and then use that to figure out the OH minus, and then the POH, and then the pH. Your equivalence point would still be controlled by the salt, and in this case, for a strong acid, strong base, or strong base, strong acid, it would be a neutral salt, so your pH would be 7. And beyond the equivalence point, your pH would be controlled by the excess acid.